Grounding and bonding are two important safety measures that are often used together to protect people and equipment from electrical hazards. Grounding provides a low-resistance path to earth for electrical current, while bonding connects different parts of an electrical system together to ensure that they are all at the same electrical potential. The National Electrical Code, or NEC, requires that all electrical systems be grounded. This is because grounding provides a safe path for electrical current to flow in the event of a fault, which can help to prevent electrical shocks and fires. The NEC also requires that all exposed metal parts of an electrical system be bonded together. This is because bonding helps to ensure that all parts of the system are at the same electrical potential, which can help to prevent electrical shocks. In the case of a land rig, it is important to use both grounding and bonding to ensure the safety of the crew and the equipment. Grounding provides a safe path for electrical current to flow in the event of a fault, while bonding helps to ensure that all parts of the electrical system are at the same electrical potential. This can help to prevent electrical shocks and fires. The NEC provides minimum requirements for grounding and bonding. However, it is often necessary to exceed these requirements in order to ensure the safety of the crew and the equipment. For example, it may be necessary to use deep rod grounding to achieve a lower resistance to ground. Grounding and bonding are essential safety measures that should not be overlooked. By following the NEC requirements and exceeding them when necessary, you can help to ensure the safety of your crew and your equipment. Now let's delve deeper into the specifics of grounding and bonding and their practical applications. Grounding, at its core, is about providing a deliberate, low-impedance path for fault currents to return to the source. This path is crucial for the operation of overcurrent protection devices like circuit breakers and fuses. When a fault occurs, such as a short circuit to ground, a large current flows through the grounding path. This high current causes the overcurrent protection device to trip, quickly disconnecting the circuit and preventing potential hazards like electrical shock or fire. The effectiveness of a grounding system hinges on its ability to provide a low impedance path. Impedance, which includes resistance and reactance, impedes the flow of alternating current. A high impedance grounding path will limit the fault current, potentially preventing the overcurrent protection device from tripping quickly enough or at all. This is where the quality of grounding connections and the selection of appropriate grounding conductors become critical. Bonding, on the other hand, focuses on equipotentiality. It's about ensuring that all conductive parts of an electrical system and nearby metallic objects are at the same electrical potential. This is achieved by connecting these parts together with bonding conductors. The primary purpose of bonding is to minimize voltage differences between conductive surfaces. If a fault occurs and a metal enclosure becomes energized, bonding ensures that any person touching the enclosure and another grounded object will not be exposed to a dangerous voltage difference. Bonding also plays a crucial role in reducing electromagnetic interference, or EMI, by providing a low impedance path for stray currents to flow. This is particularly important in sensitive electronic equipment installations. The NEC provides detailed guidelines on grounding and bonding requirements, and these requirements vary depending on the type of electrical system and the application. Let's consider some key aspects of NEC requirements. Firstly, Article 250.4a and 2 outline the general requirements for grounding grounded systems. These sections emphasize the need to ground electrical systems to limit voltage imposed by lightning, line surges, or unintentional contact with higher voltage lines, and to stabilize voltage during normal operation. Secondly, Article 250.4b specifies similar requirements for grounding ungrounded systems, highlighting the need to provide a path to ground in case of a ground fault. Thirdly, Article 250.52 addresses the use of ground rod electrodes, specifying a minimum length of 8 feet or 2.5 meters. Fourthly, Article 250.56 mandates the use of supplemental electrodes if a single ground rod does not achieve a resistance to ground of 25 ohms or less. This requirement underscores the importance of low ground resistance for effective fault current dissipation. In practical applications, achieving adequate grounding often requires more than just meeting the minimum NEC requirements. Factors such as soil resistivity, the presence of underground utilities, and the size and complexity of the electrical system can all influence the effectiveness of the grounding system. For example, in areas with high soil resistivity, multiple ground rods or ground plates may be needed to achieve a low enough resistance to ground. Alternatively, chemical ground rods, which contain chemicals that leach into the surrounding soil to improve conductivity, can be used. Deep rod grounding, where ground rods are driven deep into the earth to reach more conductive soil layers, is another effective technique for reducing ground resistance. Now, let's focus on the specific context of a land rig. Land rigs present unique challenges for grounding and bonding due to their mobile nature, harsh operating environment, and the presence of sensitive electronic equipment. The NEC requirements for grounding and bonding in land rigs are generally the same as for other electrical systems, but the implementation may need to be adapted to address the specific challenges of the rig environment. Firstly, the grounding system must be robust and able to withstand the rig's movement and vibration. Secondly, the grounding connections must be protected from corrosion and mechanical damage. Thirdly, the bonding system must be carefully designed to minimize voltage differences between different parts of the rig. One common practice in land rigs is to use a combination of ground rods and a ground ring. The ground rods provide a direct connection to earth, while the ground ring, which is a buried conductor that encircles the rig, provides a low impedance path for fault currents to flow. The ground ring is typically connected to the rig's metal structure at multiple points to ensure equipotentiality. Another important consideration in land rigs is the grounding of sensitive electronic equipment. Electronic equipment is often susceptible to damage from voltage surges and noise in the grounding system. To protect electronic equipment, it is often necessary to use isolated grounding systems. An isolated grounding system is a separate grounding system that is dedicated to the electronic equipment. The isolated grounding system is not connected to the main grounding system, which helps to reduce noise and voltage surges. In addition to grounding and bonding, other safety measures that are commonly used in land rigs include surge protection devices, or SPDs, and ground fault circuit interrupters, or GFCIs. SPD protect electrical equipment from voltage surges caused by lightning or other transient events. GFCIs protect personnel from electrical shock by detecting ground faults and quickly interrupting the circuit. Now, let's consider some specific examples of grounding and bonding practices in land rigs. Firstly, the metal frame of the rig should be bonded together to ensure equipotentiality. Secondly, all electrical equipment enclosures should be grounded to the rig's grounding system. Thirdly, the grounding conductor should be sized according to the NEC requirements and should be protected from mechanical damage and corrosion. Fourthly, the grounding system should be regularly inspected and tested to ensure that it is functioning properly. In addition to the technical aspects of grounding and bonding, it is also important to consider the human element. Workers should be properly trained on the importance of grounding and bonding and on the proper procedures for installing and maintaining grounding systems. Regular safety audits should be conducted to ensure that grounding and bonding practices are being followed. Finally, it is important to remember that grounding and bonding are not a substitute for other safety measures. Electrical safety should be a top priority in all aspects of land rig operations. Some common misconceptions about grounding and bonding are worth addressing. Firstly, some people believe that grounding is only necessary for safety. While safety is a primary concern, grounding also plays a vital role in the proper operation of electrical equipment. Secondly, some people believe that bonding is only necessary for metal parts. Bonding is also important for non-metallic parts that may become conductive due to moisture or contamination. Thirdly, some people believe that a single ground rod is sufficient for grounding. In many cases, multiple ground rods or other grounding electrodes are necessary to achieve a low enough resistance to ground. In conclusion, grounding and bonding are essential safety measures that should not be overlooked. By following the NEC requirements and exceeding them when necessary, you can help to ensure the safety of your crew and your equipment.